Hi guys, and welcome to this episode on feature importance. So what exactly is feature importance? In short, feature importance gives a score or metric that indicates how important a feature is in predicting a target variable. When constructing a machine learning model, it's useful to be able to interpret the model that we have built to understand which features contribute to our target variable prediction the most or least. So for example, let's say we wanted to predict house price, and we used 4 variables to predict that: the number of bedrooms, the distance to the closest school, distance to the closest shops, and garden size. Once we have built a model to predict house price, we can look at feature importance to figure out which is the most or least important in predicting house price. Let's say we built a model, we interpreted the model, and we figured out from feature importance that the number of bedrooms is the most important and the garden size is the least important. So this is quite a useful insight to have. So what are the uses of feature importance? Number 1, feature importance enables us to gain insight into a model. Rather than just looking at model predictions and performance, we can start to identify relationships and interactions within our own data. And secondly, understanding which features are significant or not can also enable us to build simpler models on more significant features. We may discover new relationships between our inputs and target variable or confirm old ones. So let's now delve into some of the main models and see how we can derive feature importance. Linear regression takes the following form, where y equals theta 0 plus theta 1 x1 plus all the way to theta n xn. And let's go through an example here, where y is a person's height in centimeters, x1 is their gender, so 0 is female and 1 is male, x2 is if they are above 16, 0 no and 1 yes, and we have the following theta values. And let's say we wanted to figure out, okay, is gender more important, or is the person being above the age of 16 more important in predicting a person's height? So after building the model, we just simply look at the values of the coefficients, and when using the values of the coefficients, we can determine which is the most important feature. In this case, 20 is larger than 10, that is the coefficient of gender is larger than the coefficient of if the person is above 16, so we can conclude that gender is more important than if the person is above 16 in predicting height in centimeters. In other words, the larger the absolute value of the coefficient, the more important the feature. The reason why I say absolute value is that we can have negative coefficients, and so taking the absolute value turns it into a positive coefficient, enabling us to compare coefficients to see which is the largest and which is the smallest. This only applies to features that are on the same scale. Often when we pre-process data, we normalize the data to put it on the same scale, and one advantage of this is it enables us to compare coefficients for feature importance. Let us now go through an example of logistic regression. And logistic regression takes the following form, where we have the log odds equals to theta 0 plus theta 1 x1 plus all the way to theta n xn. And let's say we found the following model, where P is the probability of lung cancer, x1 is if the person smokes cigarettes, 0 is no and 1 is yes, x2 if they do rigorous exercise once a week, 0 is no and 1 is yes. And we have here theta 0 as minus 1.5, theta 1 is 3.4, and theta 2 as minus 0.34. So as with linear regression, we can simply take the absolute values of the coefficients, and we find that 3.4 is larger than 0.34. So therefore, smoking cigarettes is more important when it comes to predicting if a person will have lung cancer. Another interesting way to look at feature importance is something called the odds ratio, where we take the exponentials of the coefficients and we can interpret our feature importance a little bit more deeply. So e to the power of 3.4 gives us something around 30, suggesting that it's around 30 times more likely to have lung cancer if you smoke cigarettes. And e to the power of minus 0.34 gives us 0.71, which is around 0.3 times less likely to have lung cancer if you do rigorous exercise once a week. Let us now look at the feature importance of decision trees, random forests, and gradient boosted trees. And let's take a look at an example where we have the feature x1, which is if a person likes exercise or not, which has two values, either 0 or 1, which we would like to split on to predict if they enjoy reading. So one way to calculate feature importance for random forests and gradient boosted trees is through something called the mean decrease in Gini impurity. Gini impurity is given by the following formula, where P is the probability of class I and N is the number of classes. So you can sort of think of it as how pure a certain node is. So if it is completely pure, then we have everything in one class. And so if we had two classes, P1 would be 1 and P2 would be 0, giving us an impurity of 1 minus 1, which is 0. So that is the Gini impurity is 0, and so the node is completely pure. And we can think that the maximum value or the maximum impurity of a node is when we have an equal mix of two classes, and when P1 is a half and P2 is a half, we get the maximum value of Gini impurity, which is a half. So going through the example here, to calculate the decrease in Gini impurity, we look at the first node and calculate the Gini impurity here, which is 0.47. And we also calculate the weighted Gini impurity of the next two nodes, which is 0.365. And so the decrease in Gini impurity is 0.47 minus 0.365, which is 0.105. So ideally in a decision tree, we want big decreases in impurity because this suggests that we're sorting the data well. So this was for a single instance. In random forests and gradient boosted trees, we have many decision trees that are being built, and the same feature can be split on multiple times. Hence we take the mean decrease in Gini impurity as a measure of feature importance. In summary, for decision trees, random forests, and gradient boosted trees, we look at the decrease in Gini impurity for a given feature to determine feature importance. The larger the decrease in Gini impurity, which is sometimes the case in decision trees where you're only looking at splitting on a single feature, or decrease in mean Gini impurity, which is often the case in random forests and gradient boosted trees, where you often split on the same feature multiple times, the more important the feature. So the larger the decrease in Gini impurity or decrease in mean Gini impurity, the more important the feature. Another method for calculating feature importance is through something called feature permutation. This doesn't just apply to decision trees, random forests, and gradient boosted trees, but also other machine learning algorithms. Let's say we constructed a model and we looked at the cross-validation set. Here we have the height, the weight, and the gender of an individual, as well as the predicted values. In this particular cross-validation set, we have an accuracy of 0.86. With feature permutation, we select a feature in which we would like to calculate its feature importance. And let's say height in this example. And we randomly shuffle the values within this column whilst keeping all other columns constant. We then see how do our predictions change with these difference in height values. And in this case, we're looking at the accuracy. So here we see a decrease in accuracy. We can apply the same method to the weight column. And we see another decrease in accuracy. Now to determine which feature is the most important, we simply look at which feature resulted in the largest decrease in accuracy when shuffling. In this case, it's height. For decision trees, random forests, and gradient boosted trees, another method for calculating feature importance is by looking at the number of times a feature is split on. The more times a feature is selected to be split on can also be an indication of the feature's importance. The more splits on a particular feature, the more important the feature is. Lastly, let's take a look at neural networks. For neural networks, we can use feature permutation as discussed previously. We can also look at something called SHAP, which is a method that uses a game theoretic approach to explain the output of a machine learning model. Each feature is given a value that indicates its importance in contributing to a model's prediction. So a positive SHAP value indicates a positive impact on a model's prediction, whilst a negative SHAP value indicates a negative impact on a model's prediction. It can be applied to linear regression, gradient boosted trees, or any other machine learning algorithm. Thank you very much for watching, and I hope you learned something new.